Hi, today we would like to learn about chapter 3, which it is for second order circuit, and today's topic is about the initial and final value. Okay, let's go to the learning objectives. At the end of the chapter, students should be able to determine the natural response and the step response of a parallel RLC circuit. And the second one is to determine the natural response and the step response of the series RLC circuit, meaning that we will have two types of RLC circuit. One should be the parallel RLC and the other one should be the RLC. Should be the series RLC. Alright, let's move to the introduction. In the previous chapter, we considered a circuit with a single storage element, a capacitor or an inductor in RL or RC circuit. And such circuits are actually called as first order because of the differential equations described them are the first order differential equation. In this chapter, we will consider circuits containing two storage elements. Since there are two storage elements, so it is easy for us to understood that this should be known as a second order circuit because their responses are described by differential equations that contain second order derivatives. So, meaning that a second order circuit is characterized by a second order differential equation. It consists of resistor and the equivalent of two energy storage elements. Okay, now let's look at the RLC circuit example. What are considered as RLC circuit? A typical examples of a second order circuits are RLC circuit as shown in figure 1A and 1B. You can see in figure 1A, this is actually a series RLC circuit which the R, L, and C are connected in series with the voltage source. So you can see that if the current is in series with this, so you can consider the connection is in series. As for the figure B, you can say that this is an RLC circuit in parallel due to the parallel connection of each of the elements, and you can see that each of these elements has different current, but of course it shares the same voltage drop. Other examples are RL and RC circuits, but how do we differentiate this from a common RC and RL circuit in first order? So you can say that in figure C, you have two resistors and you also have two energy storage elements L1 and L2. So this is considered as second order circuit. Okay, the same goes for figure D. Although you have RC circuit, but since your energy storage elements appear two times, C1 and C2, so the analysis in the circuit should be carried out with a second order differential equation. So meaning that whenever you see in the circuit, you have two energy storage elements, the same elements like component or inductor or capacitor, so it's still considered as second order circuit, right? So the elements of the same type cannot be represented by an equivalent single element. For example, if you have two capacitor here, you cannot find the equivalent C equivalent to consider it as one single element. Our analysis of second order circuit will be similar to that used for first order circuit. Perhaps the major problem students face in handling second order circuit is finding the initial and final conditions on the circuit variables. Students are usually comfortable getting the initial and final values of V, which is the voltage, and I, the current, but often have difficulty to find the initial value of their derivatives, which come by using the dv dt and di dt. This is the part which a bit different from the one that you use to solve first order circuit, because in here you need to find the derivatives of voltage and current at initial condition. Anyway, the key point to determine the initial condition can be divided into two. So you should carefully handle the polarity of voltage Vt across the capacitor, and of course you need to understand the direction of current through an inductor. Okay, and for the capacitor voltage, this is again, it's a basic from chapter 1. So it's always continuous. So you can say that V0 positive at this instant the switch connected or open at t equals to 0 should be similar to the one that you find V0 negative. Okay, and the inductor current, it's always continuous, so that I0 positive equals to I0 negative. These two you must take care of. Alright, and a second order differential equation is required to solve for the voltage across or the current flowing through a component. So the circuit will contain at least, you know that a second order circuit, for the circuit it should contain at least one resistor and the equivalent of two energy storage elements, such as you have two capacitors in the circuit, or maybe two inductors in the circuit, or maybe you have resistor, a capacitor, and an inductor. That is about the boundary condition. Okay, remember that in chapter 2 we also learn about initial or steady state response, and also you also learn about the initial value, and then you find the transient, and also you find the steady state. For a step response function, ut minus t naught, okay, remember this is the unit step function, for all times between t equals to plus meaning that started just after t equals to 0, and at minus infinity except for some time period after t equals to t naught. So t naught is the initial condition at t equals to 0. And remember, during this time capacitors are open and inductors are in the short circuit. Okay, and during the transition at the step t equals to t naught, forgotten about this. This is actually the thing that you should do whenever you apply the DC analysis, so that all the capacitors should be open and all the inductors are short circuit, so that you can find current over here and you can find voltage at the capacitor. Okay, next, during the transition at the step t equals to t naught, voltage across capacitor is continuous, so you just take this value, which is similar to the one that you find the initial condition. Okay, and the same for the current through an inductor is continuous, so we can consider the ILT0 positive equals to ILT0 negative. So this one is the t less than 0, and this is just after t equals to And then what you need to do is you need to redraw the circuit at t less than t0. So meaning that if our t0 is 0, so you need to redraw the circuit at t less than 0. Remember that in chapter 2, we need to consider 3 timelines at t less than 0, at t equals to 0, and also at t greater than 0. Okay, so it's the same condition over here. Next is you need to determine the value of all voltage and current sources at t less than 0. So this is the condition at t less than 0. Find the voltage and current source value. Then you make the appropriate substitution for the energy storage devices. So let's say you see a capacitor, so you substitute with open circuit, which it gives the current 0, but there will be a voltage. And for the inductor, you substitute the inductors with short circuit, which gives you voltage equals to 0, but there should be a current. And then you need to calculate the VC and IL at t less than t0, meaning that VC and IL for t less than. Next is you need to find the final condition. Final condition means the steady state or the, at infinity. So you need to redraw again the circuit at t equals to infinity, the steady state, and you need to determine the value of all voltage and current sources at t equals to infinity. Then you make the appropriate substitution again, similar to the one that you used just now. For all the capacitor, apply open circuit, and for all inductors, you applied a short circuit. And then you can calculate the VC steady state and IL steady state, or VC infinity and IL infinity. As for the summary on this boundary condition or the initial and final condition for second order circuit, so you need to know the magnitude of voltage and current sources in the circuit before and just after a step function is applied. So in a steady state at t less than 0 and t equals to infinity, you replace the energy storage devices for capacitors with open circuit and inductors and as a short circuit. Okay, and then you need to calculate the voltage across capacitor and the current through the inductor. As for during the transition at step t equal to t0, remember that voltage and current through your energy elements are continuous, so we can consider these two values, which is your VC T0 plus equals to your VC T0 negative. Okay, the same goes to the current through your